Well, it's my great pleasure to introduce Brendan Shapiro, who will today be telling us about double copresheaf categories for your polynomial functors. Take it away.
All right, thanks so much, Bryce and Tim, for organizing this and inviting me. I'm really enjoying this conference so far and excited for speaking here and seeing all the rest of the talks. So this is just going to be mostly expository because there are a few results joint with David that I want to tell you about, but in order to get to there and place them in the context of why we think they're so interesting, there are many other things that we have to cover first. So hopefully this will be something of an introduction to this area of polynomial functors and some of the ways that we've been thinking about them for the purposes of double categories and also databases. So first I'm going to tell you about databases, and this is all based on David's work going back for many years now. I'll make sure I provide references in the notes at the end. So the idea is we could start with some data table. So here I'm using the example of a graph where we have a graph, it's got some vertices and some edges, and we can organize those or visualize that in a data table. And this could be useful for talking about graphs computationally. So in the table, we have rows, and each row is really its own unique thing. We have a morphism F, G, H, and K. There's a column in this table which gives you the names of these things. So they have a unique, each row has a unique identifier in the table. One thing not drawn is you also would have a table of vertices. So that would be its own table. So there are 3 vertices, and you don't need any additional information for that because the vertices don't carry any information other than their name. But in this first table, we do have some extra information. Each edge has a source vertex and a target vertex. Now, in some versions of databases, these tables describe relations, but if you insist that each row has a name in the leftmost column, then you can think of each column as a function from the set of rows in this table, in this case, edges, to some other set. In this case, the set of vertices or rows in the vertex table. And this is something rather familiar to category theorists, that a graph is a functor from this category with 2 objects and 2 morphisms. So you have an object for the edge and for the vertex, and each edge has a source and a target. And so if you take a functor from there to set, that gives you a graph. And so the premise of a lot of David's database theory is that you can do this for very general database schema, that a database schema is really just a category where the objects are the tables and the morphisms are the morphisms out of one of those tables is a column in that table. So for each row in your table, for each row in your table, you get a row in some other table for each column, if you sort of add in all the tables that you need to make that make sense. And so in this sense, databases can be modeled as copresheafs. And so I'll just introduce a little notation. I'm going to write C set for the category of copresheafs on C, by which I mean functors from C to set. I'll also apologize that in my original title, I said presheaf double categories, but this is really going to be all about copresheafs. If you're like me and more used to using presheafs, then I encourage you to insert ops wherever you like. So the next thing I want to define is a query. So in database theory, it's a common thing you have a bunch of tables that we call a database, and we want to query them to extract some information from them that isn't necessarily encoded in any single one of the tables just yet. And so in this formalism, I'm going to define a query as a functor to set, which is a disjoint union of representables. So in the case of our graph database, example, so first of all, when I say representables in graphs, that makes sense what that would be. These are just going to be graphs. But for general databases, these are going to be essentially models for the type of information that you're looking at. But I'll give you an example in graphs where these representing objects or arities, E sub t, are going to be the walking paths of length m. And so we can define a functor from the category of graphs to set, which sends a graph to the set of all paths of length less than or equal to n. And so that's what we do over here. And it's a disjoint union of representables because paths of a fixed length m are given by maps of graphs from the walking length m path into your graph x. But we might want to allow paths of different lengths. For instance, they could go up to n, or we could pick any of them. Most interesting to category theorists is usually where we allow paths of all lengths, because that gives us part of the free category functor on graphs. But here we're just going to set. So we would just be picking out the set of paths in X. And these are analogous to queries on a database. And you can work out like various standard operations. And databases like joins are of this form. And this is discussed in David's database papers. So we can level this up, so to speak, by instead of querying a database to get a set, we can migrate data from one type of database to another. So if we have a database with schema C, we can convert that into a database of schema D using queries for each object in D. So that's what I've written here. We take a database of type C and we send it to a database of type D where the rows in each of the D index tables are queries of the C index database. So I'll give an example of, well, before I give an example, I'll just mention the data that goes into this. So in order to do this, you need to have queries and they need to be compatible, though you can get some of that for free by naturality. So whereas in a query, we just needed a set of databases of type C or C copresheafs. Now we need that for every object in D. And so those sets are going to vary functorially in D because we have functions from the set of arities for an object D to the set of arities for an object D prime for every morphism in D. So the punchline is that the information we need amounts to a functor from D to set and a functor from the category of elements of that to C sets. Now, I know I've gone through this kind of fast, and I apologize for not being able to get into this in a little bit more detail. But the point of mentioning this, I'm not going to get too much more into the specifics of databases because the goal of this talk is to focus on polynomial functors and copresheafs. But the point of this is that functors of this form are useful in database theory in that they model various forms of traditional queries and they correspond to something relatively mathematically elegant. in that these are functors between copresheaf categories, which have appeared in various places in the literature, are fairly nice to define because they only rely on this sort of combinatorial data of you have some sets and you have some arities, which vary functorially in D. And it also includes various functors that are of a lot of interest to category theorists. So I mentioned the free category functor on graphs. And so this can be thought of as a data migration from graphs to graphs. So here we're not changing the schema. And what it does is on edges, you send a graph X to a new graph whose edges are paths in X. That is a disjoint union of representables. And the vertices of the new graph are the same as your original graph, which is a single representable represented by the vertex. And so this is my favorite example of a data migration functor, or I like to call them familial functors. And you get these for lots of different types of higher categories, like there's a free 2-category functor on 2 graphs, or a free double category functor on double graphs. And all of them are defined in an analogous way as a disjoint union of functors represented by arities, the types of things that you want to be able to compose. But that would be the subject of a different talk. I'm going to pause for questions here about the database motivation before I go on. Feel free to interrupt at any point. These types of databases are fairly well developed, and I'm going to spend some more time talking about some of the ways in which that theory has been developed. But the hook for this talk, and something that I think that our results are hopefully going to be useful for, is talking about a more general type of databases based on double categories. So the idea is that instead of using functors to set, where we have some list of tables and a sort of deterministic relationship where each row in a table has a specific entry in each column, we also sometimes have relationships which are more relational, where there's not like where it's not a function. There's not a single thing that you go to, but a relation between different types of objects. So an example of that would be like so. So here I've drawn a very tiny double category, which is a double category may not be very interesting, but it's all in the interpretation. So if we have objects for people, for companies, and for locations, places, then, and I want to think of what a double functor from here to rel is, where rel has sets as objects, functions as vertical morphisms, and relations as the horizontal morphisms. So we can think of these arrows as functions and these ticked arrows as relations. And the two cells are inclusions of relations. Then what this is saying is that we have a set of people, each of them lives in a single place. We have a set of companies, and each of them is based in a single place. Maybe that's not fully general the way companies work, but we can pretend that it is. And then we have a relation between people and companies where people don't necessarily work for a single company. Maybe some companies don't have employees, maybe some people aren't working. That's more of a relation than a function, unlike where you live, which is, at least in a simple example, a more functional type of relationship. And so what this arrow is saying is another very specialized assumption here, which is that if I'm a person working for a particular company, then I live in the same place where that company is based. Now, we would probably want these to be cities rather than like buildings, but that's a stronger assumption. You could interpret that, for instance, as not allowing remote work. Any company I work for has to be based in the same place that I am, and that's because the identity, we have a map from the employment relation to the identity relation on places. So any person employed by a company, their locations have to agree. And so you can encode a lot of information like that in the double category. And in the notes that go on the website, I'll include a link to Michael Lambert's blog post on the Topos website, which talks about a lot more examples of these, again, using rel. I'll also mention that mathematically speaking, there's no reason why it would have to be rel as opposed to span, where the horizontal morphisms are spans of sets. Though at the moment, I don't think I have any particularly interesting example for that. But you can imagine upgrading these, like maybe you've worked for a company in different times or in different roles. That might be a reason to use spans instead of relations. So this is the motivation, or a motivation, going into what will be a pretty much pure math talk for the rest of the time. So maybe before I start that, I'll pause again for questions. All right. So before we get to polynomial functors, I want to tell you a different way of thinking about categories and copresheafs, which is going to be a bit of a warm up for how we like to think of these when we are working with polynomials. So I'm going to define categories for you, which is maybe not something you would expect me to do in a talk like this, but it's going to be different than what you're used to. So we still have a set of objects. That hasn't changed. That's hard to avoid. But now, instead of defining our morphisms in terms of their source and their target, or other approaches where you just have like a set of morphisms and you decide on their sources and targets later. Here, we're going to define the morphisms only by their source. So we have these sets, which I've written as big C bracket little c. And those are going to be the sets of all outgoing morphisms from a single object, C. And so now if we want to recover the definition of category, well, we need to know their codomains, because ultimately we're trying to get the same information here. So codomains are encoded as a function from the set of arrows outgoing from C to the set of objects. Identities are not so hard. It's just a single element of each C bracket C. And while I'm not writing out all of the equations here, we would also expect the codomain of that arrow to be C, the same as its domain. And then finally, we have composition. And this one maybe looks the strangest. It's saying that for every, we have a function from the set of pairs of a morphism out of C, which I write as F, and then we can take the codomain of F to get a new object of C, and then we get an outgoing arrow from there. So I'll draw what this looks like. So if we have an object C, and then arrows F, maybe G, then we take their codomains, and we get new objects. And then we take arrows out of them. And what this function is saying is that for any pair of arrows like so, we get a composite. Draw all of them in here. I don't want to draw. And that's what this composition function is doing. It's the same composition that we would expect in the usual definition of category, in the two adjacent morphisms have a composite. It's just treating them using the indexing scheme based on domains rather than domains and codomains. And then we have unit and associativity equations that I'm not going to write down, but are a straightforward exercise, which say things like, we have any of these pairs, an identity composed with another arrow gives you the same arrow, and the composition is associative in the sense that any three arrows compose the same in either way, which can be expressed in this language, though I don't think it's particularly helpful in this scenario. So we can take this perspective a little further and say, okay, well, we've defined categories in this way, but we're interested in copresheaves, and maybe there's some different way of defining them, which will be more aligned with this definition. So for that, we're going to start with just a set. And I want you to think of this set as all of the elements in a copresheaf, sort of forgetting about the indexing objects. Then now we don't have to forget about the indexing objects. We just encode them as a function. So I called this type. That's not particularly standard or anything, but the idea is that each element of X lives over some object in C. And so this is just like a copresheaf where, an element is part of a set that is assigned to each object in C. And then the challenging part is to encode the structure maps in the copresheaf. And so here what we're saying is we have an element X, and for we have an element X, it has a type C, which is an object of our category. And for every outgoing arrow from that object C, we have a new element of X, which is exactly what you would expect in a copresheaf. We have there, the usual definition defines these in terms of functions between the sets of elements over each object in C, but you could just as well do it for each element and then have a function from the set of outgoing arrows. And of course, you need conditions, as always, to make sure that the codomains work properly and identities and compositions are treated appropriately. I'll also move over a more concise comparison. So this is just saying that if we have a copresheaf defined as a functor from C to set, which I call Y, then the set X of elements is the disjoint union of each of those sets YC. The type function just sends each element to the underlying object in C, and these action functions send a morphism to the application of that morphism by our copresheaf. Questions on this?
There's a question.
Is this related to discrete vibrations? Because it seems to be just like kind of the protein deconstructional category of elements of the copresheaf.
Yeah, it definitely is. I think, hopefully I don't butcher this. I wasn't really planning to talk about cofunctors today, but those are closely related. And so so part of that relationship would be that since a copresheaf on C corresponds to a discrete op fibration over C, and a discrete op fibration over C is a particular kind of cofunctor. And so here we're sort of using the cofunctor structure. And yeah, you can find a condition in there that makes it a discrete op fibration.
So it's not exactly the same thing.
It is the same. So what we're describing is the same thing as a discrete op fibration. Is it the same sort of on a syntactic level as definitions? Maybe. I mean, it definitely looks very similar in that, you know, for every outgoing arrow, we have a unique thing. I guess that's kind of a subjective question, but I kind of.
Okay, thanks.
Yeah, I like that way of thinking about it. I wrote out this definition mostly just to somewhat facilitate the theorem I'm going to mention in a few minutes without proof. So hopefully this gives a sense of a different way of thinking about copresheaves, though. Yeah, this really does feel closer to discrete op fibrations than the functor perspective. Yeah. And I think there's some deep reasons. Anyway, unless there are other questions, I'm going to start talking about polynomials. So I'm going to say something terribly rude to any algebraists, which is I am just going to say the word polynomial to describe a set, which I'll write as P of 1, and a family of sets over it, indexed by it, which I'm going to write as P bracket I, where I is an element of P of 1. Why would I call such a thing a polynomial? Because it has an associated functor from set to set, which sends a set X to a disjoint union of exponents of X. It's actually very common to write this using a summation sign to really push the analogy. But it's a disjoint union of representable functors on set, represented by these sets P bracket I, though we're going to go back and forth between thinking of it as just a family of sets versus an endofunctor on set versus a bundle of where we take the disjoint union of all of these sets and project back down from there to P of 1. These are all equivalent in basically a similar way as the copresheaves, though we're not going to use that because our sets P of 1 can vary. And so the interesting part of polynomials is not so much their definition, which is very simple, but what it means to have a morphism between them. Now, these morphisms are defined relative to the endofunctors on set. They correspond precisely to what it takes to define a natural transformation between these things. So you have a forward pointing function from P of 1 to Q of 1, just like a natural transformation between functors of this form, we would have a forward pointing function from the indexing set of this coproduct to the indexing set of another. So when I say that, I mean, if we were to map from we were to map from this polynomial functor to another one, we would need a function from P of 1 to Q of 1. But then to get functions, forward-pointing functions on these exponential objects, we need backwards-pointing functions on their representing sets. So that's why we have functions pointing backwards from Q bracket Bi back to P of I. I'm not going to get into this too well. No, this will come up a few points. There's a lot of literature on this category of polynomial functors. It has a lot of nice structure. In particular, the one I want to mention now is that polynomials can compose, which when we think of them as endofunctors is very clear, but it's nice to have an explicit formula for what that composite looks like. And in particular, an element of P composed Q of 1 is a pair of an element I in P of 1 and a function from P bracket I to Q of 1. And you can check that this agrees with like as classical composition of polynomials as you like. And then for our exponents, or directions, as we sometimes call them. So given an element of P composed Q of 1, we call those positions. So that consists of I in P of 1 and J mapping from P bracket I to Q of 1. We have just an element of P bracket I and an element of Q bracket Ji, dependent on that first choice of little I. This gives us a monoidal structure along with the identity, which if we think of these polynomials just as variables is just y, if we use y as a variable. But that is the one where y of 1 has a single element and its exponent also has a single element. The fact that this is a unit for composition corresponds to the identity function regarded as a polynomial being the unit for composition. So we get a monoidal category this way, which you are sort of free to think of as either polynomial endofunctors on set with the identity and composition, or these more direct formulas for what these things look like as families of sets. And now that I've defined that, I can start stating some very powerful theorems that have come up in recent years. So a result of Ahman and Uustalu is that a comonoid in this monoidal category, by which I mean a polynomial P with a map to Y and a map to P composed P, satisfying unit and associativity equations, is the same information as a category. Which, if you haven't seen any of this before, may come out of nowhere. So I'll break it down just a little bit. So if we start with a category C, and we really want to think of this in the coalgebraic way that I wrote out above in terms of outgoing arrows. We start with the category C, then P of 1, our positions, are going to be just the objects of C. And P bracket C, for such an object, is going to be the set of outgoing arrows, which is why I wrote C bracket C when defining categories. And so where does the structure of a category come from in this? Well, if we have a map to Y, the forwards map on positions doesn't do anything because Y only has one position. You don't have any choices there. But the backwards map, you need a map from the singleton to each C bracket C. Those pick out your identity arrows. So next we have the co-multiplication of the comonoid. And if we just look at the part on positions from P of 1 to P composed P of 1, we have a map from objects in C to the disjoint union over objects in C of maps from outgoing arrows at that object to objects. And that's a little bit more complicated than we necessarily want, because we actually have imposed by the comonoid laws that if we start with an object C in here, that is sent to the pair of the same C along with one of these functions from C bracket C to the objects in C. And so if you'll permit me to assume that, then this gives us the codomains. For each object in C, we get a function from C bracket C, the outgoing arrows, back to the objects in C, which is precisely the codomain functions that were part of this definition of categories. And then composition is going to look more similar to what I defined above once we restrict it to a particular position. So generally a map from P to P compose P consists of a function from P compose P of the image of I back to P bracket I. In our case, this is a function from the disjoint union over all outgoing morphisms from an object C of outgoing morphisms of objects in its codomain. So these are the pairs in this picture that I drew above. We have a function from there to C bracket C, which is exactly what that composition looked like. And so the way this works is, even though we're mapping from P to P composed P, which seems kind of like the opposite of something that would give you a composition, because the arrows on the directions point backwards, the arrows on the outgoing morphisms point backwards in the definition of morphisms of polynomials, this does give us a composition operation from pairs of adjacent arrows to arrows, where we're only fixing the domains in our indexing scheme. And then I'll just conclude this sketch by mentioning that when we think of this polynomial P as a bundle, the map here is the source map, which makes sense. Our directions at an object C are all the arrows, but that is their source. And so this gives us, as a bundle, the source function from morphisms in C to objects in C. And I'll provide citations for where you can find this written up. Questions on that before I move on? So what I'm basically going to be doing for the rest of this talk is something my wife likes to make fun of me for, which is saying, a this is just a this. So here I said that a composition comonoid is just a category. There's a lot more of that follows from this first one. So next version iteration, when we have a composition comonoid, by which I mean a category, and we remember that it starts out with a polynomial, so we have an endofunctor on set. A coalgebra for that functor, which is a map from X to C of X, where C of X is defined like this, is the same as a copresheaf. And the way that works is, well, a copresheaf needs a set X, a function assigning each element of X to an object in C, and an action of the morphisms of C on X. And so here, this function has a set X. The function to C of X includes a function that picks out the objects in C. And then for each And then for each element x, you have a map from the outgoing arrows at the corresponding object of C back to the set X. So it's the same information. It being a coalgebra implies all of the equations that I didn't write down when defining a copresheaf. It ensures that all of them hold, that this respects codomains, identities, and compositions in an appropriate manner. And we can take this even further by a theorem of Garner. So given comonoids, C and D, we can define what are called bicomodules, where a bicomodule is a polynomial P with maps to C composed P and P composed D, which satisfy various equations that I'm not going to tell you. And for reasons that will become clear in a moment, we like to think of this as a bicomodule from D to C. So I write this as this sort of blocky arrow from D to C. And Garner's theorem says that this is the same thing as a familial functor from D set to C set. So these are the data migration functors that I mentioned earlier on. And the idea behind this is that a coalgebra for D, you can check that that's the same thing in some generality as a comodule, which is the same as a bicomodule from the empty category. And so when we're looking to define this functor from D sets to C sets, well, D sets are just these coalgebras. These coalgebras are bicomodules from empty to D. We get a functor by just composing bicomodules, composing X with P. And you can check that it has the form of a familial functor. Basically because in all of these definitions, including definition of polynomial and everything we see here, there are disjoint unions of representables. So that is everywhere throughout this definition. And the we also know other things that like bicomodules compose in this setting, and that their composition agrees with the composition of familial functors. And you can find this described in David Spivak's functorial aggregation paper that I'll write down at the end for the notes. So for the sake of time, I'm going to speed up just a little bit to get to the main result, but we're pretty close. So before that, I'll just mention that in a very general, in a, let's say a monoidal bicategory, comonoids and bicomodules form the 0 cells and 1 cells of a bicategory. In fact, it's a double category if you include homomorphisms of comonoids, which are not functors, but cofunctors. That's an interesting double category, but that's not what I see as the hook for talking about this at a double categories workshop. So I'll just focus on the bicategory, which is equivalent to the 2 category of copresheaf categories over small categories, familial functors between them, and natural transformations. This is, I don't think this is actually done in full in the literature. Something close to it is in my thesis, and the main ingredients of it are in David's functorial aggregation paper. But what this says is that polynomials can model in a very elegant way, just using these categorical constructions of comonoids and bicomodules, the copresheaf categories and familial functors that arise in database theory. And so the point of this talk that I've now finally gotten to is to say that we can do the same thing for double categorical databases by upgrading our notion of polynomial. So what do I mean by that? Well, polynomials had all of these different definitions. I'm going to pick one that's convenient for me, namely the bundle definition. So I'll use similar notation because it's more general now. I'll use the summation symbol, where we define a polynomial as a morphism in a category A, which I will ask to have finite limits. And we want that morphism to be exponentiable. I'm not going to have time to tell you what exponentiable means, but it's a fairly standard condition. It corresponds to what are called Condorcet functors when A is capped, and those include vibrations, off vibrations, and lots of other nice functors. And so we get a monoidal category, just like polynomial functors on sets, where composition is defined by a similar formula to the one that we used for ordinary polynomials. You also get endofunctors out of this, but they're not quite as easy to characterize in general. So the bundles work better as a definition. So the first theorem that I'll mention from David in my work is that if we look at polynomials in the category of categories, then a comonoid for the composition monoidal structure is the same thing as a strict double category, where the bundle map of that polynomial is the source functor from D1 to D0 in the at least one of the standard definitions of double categories. The only thing is that that source functor, because of the way we've defined polynomials, that source functor needs to be exponentiable. And you can't really avoid this when you're doing polynomials. If you want them to have composition, you need exponentiability. But I will excuse this somewhat by mentioning that lots of examples of double categories have this property. So any framed bicategory slash vibrant double category slash equipment has this property. In fact, an even stronger property. Commutative squares in a category have this property, which corresponds to a certain type of factorizations. And we've found lots of other double categories which have this. I wish that I could say that like every double category that arises in practice or in common practice has this property. We have found one or two that don't, but it's really not terribly restrictive for the things that we've been interested in doing. And while this is a work in progress, when our paper comes out, we'll include lots more examples. And so the basic idea here is that D0, that P of 1, the positions, or the base, lots of different words for this, is the vertical category. I call D0 the vertical category. I know that's not universally agreed upon. The bundle map of the polynomial is the source functor, like I mentioned. And what the comonoid structure is doing, it told us how to define composition and identities when we were showing that these agreed with categories in ordinary polynomials. Here, it gives us horizontal identities, codomains, and composition, where the vertical ones just come from the fact that both of these, P of 1 and the total space, are already categories. So that's where the vertical structure comes from. Now I'll just finish by finally talking about double copresheafs. So those are defined as lax double functors. So they're lax in the horizontal direction from D to span, whose objects are sets, vertical maps are functions, horizontal maps are spans, squares are maps of spans. And some examples of this, these are fairly general things, and they recover a lot of nice things from category theory. When D is the when our double category is a one category in the vertical direction, so it is horizontally discrete, then we just get an ordinary copresheaf because we're mapping into the vertical category of span, which is just set. When D is a category pointing horizontally, then it's a lax functor from there into span. That is equivalent to a functor of categories into our one category. And I'll also mention, since I talked about rel before, and double functors into rel, is where a lot of our examples of databases come from. A double functor into rel, strict or lax, gives us a lax functor, double functor into span, because there's one of those from rel to span. So then finally, I'll state the main theorem, which is that when we have a composition comonoid in polynomials in cat, which is a double category with this property on the source functor, then a bicomodule, a composition bicomodule from 0, which for ordinary polynomials was a copresheaf. Here it is also a copresheaf, except on the transpose of D. These are strict double categories. We can do pseudo comonoids, which would give us pseudo double categories, but that would make this theorem a lot harder to talk about because we want to be able to take transposes. I won't have time to work out the details of this, but I will mention that similar to Garner's result, you get functor, any general bicomodules between these double categories gives you functors between, in fact, double functors between double copresheaf categories, which are in analogy with familial functors in that they look like a disjoint union of exponents in the same way that familial functors do. And the hope is that this theory for double categories will have implications for databases, that it will provide a convenient framework for talking about data migration functors between double categorical databases. And also, there's also lots of other reasons why familial functors between ordinary copresheaf categories are nice that might extend to here as well. And with that, I will thank the organizers again and finish up.
Okay, thank you very much for your talk. And we'll get some lots of applause in the Zoom. Does anyone have any questions for Brendan?
Looks like Bob has his hand up. If you want to ask Bob.
Yes. So I'm just trying to understand this exponential condition. So suppose you go back to sets, but instead of taking the category of sets to do your polynomials in, you took, let's say, just countable or finite set. So finite and countable. So sets of cardinality less than or equal to L naught. Okay.
Sure.
And so you would get polynomials that way.
Yeah.
And you could compose them presumably. So then would the comonoids in there correspond? So not everything is exponentiable in there, right? If you take a countable set to a countable set, then it's not countable, so it's not in there. Okay, so not everything is exponentiable in there. So would you get categories in which the domain function is exponentiable? Do you understand what I'm saying?
Yeah. So yes, that's a great question. So this result holds in some generality. We're still pinning down exactly what that is, but essentially, if A has finite limits, we need pullbacks, and a terminal object to define y, you get I believe you get an analogous result. I want to avoid saying anything that will turn out to be wrong about exactly what level of generality. But I think what you would want to expect is that, yes, in nice cases, which I'm fairly sure the ones you mentioned are, and I mean, I know finite sets are, then you would get that a comonoid is going to be a category internal to A, where the source functor is exponentiable.
Okay, yeah, thank you.
And we have a couple of questions in the chat. I don't know if you can see that, Brendan, or not.
I haven't.
Okay, so I can read them out. The first question was answered, so we won't do that. But the second question is it possible to relax the familial representability condition on the bicomodules to something slightly more general than polynomials, is the question.
Yeah, so I know that in a lot of the literature, things like analytic functors show up in a lot of places. Those have a lot of nice properties. Though as far as we know, you cannot get those by a similar means to this. You can, yeah, I'm not aware of a way to do that within, like, you know, as elegantly in the polynomial framework. Like, certainly the definition is not so different. You just quotient out the Hom sets by some automorphisms. And of course, there are other generalizations that I might not be as aware of. But if the motivation was to ask about analytic functors, then I don't think so. At least not in a way as nice as this. Otherwise, I'm not sure.
Okay, the question asker is happy with that response, so thank you.
Glad to hear it.
Any other questions for Brendan?
The question says something more general than polynomials. That would be cool. This part of the question, but yeah, and I mean, one thing that we are looking at is that when you use these polynomials in cat rather than set, you can get very general things. Like, I didn't talk about monads here in sort of like familial monads or bicomodules with monoidal structure. But that's where you get a lot of these applications to sort of free category or free higher category monads and relationships to operads. And in categorical polynomials, you can model fairly general, or at least much more general things than just the sigma free symmetric operads that polynomial monads can do.
Okay, great, thank you. So let's thank our speaker again.